Hello again. This is Math 2232 coming to you from the College page, and this is the conclusion of the lecture on improper integrals. As always, please be an attentive learner while watching this video. The first part of this lecture talked about improper integrals, where the reason it was improper was the interval of integration is infinite. This one talks about the situation where there's a discontinuity in the interval of integration, either at one endpoint, the other endpoint, or somewhere in the middle. And you can also have integrals where they're doubly improper. We'll see an example of that in a bit. Okay, so we're looking at the second type, and these are integrals that have discontinuous integrands. The process here is basically the same with one subtle difference. And so if f is continuous on the interval AB, now notice that this is closed on A, but B is not included, so it's discontinuous at x equal B. That is the right endpoint. Then the integral from A to B f of x dx, because of the discontinuity, is going to be the limit as t tends to b from the left. You can't really see that, but that is from the left. And this goes from a to t, f of x dx. So as you see, this is a limit from the left for the right endpoint, provided the limit exists and is finite. If f of x is continuous on the open a, closed b interval, that means not continuous on x equal a, then the integral from a to b of f of x dx is the limit as t tends to a, this time from the right. You're always going from the inside of the interval. This goes from t to b, f of t dt, provided the limit exists and is finite. If f of x is not continuous at x equals c, and c is in between, then, and the integral from a to c f of x dx and the integral from c to b f of x dx are both convergent, then the integral from a to b is equal to the integral from a to c f of x dx plus the integral from c to b f of x dx. Now note that this integral here was really the first type that we talked about, and this integral is for the second type. So as with the infinite integral case, this requires both of the integrals to be convergent in order for this integral to also be convergent. If either of the two integrals is divergent, then so is this integral. You need to think about this a little bit in conjunction with the 1 and 2. Finally, if f of x is not continuous at x equal a and x equal b, and the integral from a to c f of x and the integral from c to b f of x dx are both convergent, then this integral is equal to the integral from a to c plus the integral from c to b, where c is any number. Again, this requires both of the integrals to be convergent in order for it to be convergent, and if either of the two integrals is divergent, then so is this interval. And you really need to think clearly about, because there are four cases, but they're subtly different. And make sure that you're using right or left-handed limits. And I should have said, and I did have it in red, that this integral is more camouflaged than the others, because you don't have an infinity staring you in the face. And in fact, here's an example of camouflage. There is a snake in this picture that you don't see unless it's highlighted in this picture, and this snake is a copperhead, way venomous. So be careful about these kind of improper integrals. So we're looking to have an example. So we're to evaluate the integral from 0 to 1 of dx over the cube root of x. You know what to do. Let's see how you did. Okay, now this function, here's the graph, has an infinite discontinuity at x equals 0. That's the left endpoint. So what you have to do is say the integral from 0 to 1 of x to the minus 1/3 dx is equal to the limit as b tends to 0. And this is from the right. You add 1 to the exponent, divide by the new exponent, you get this. And you put b here because that's replacing the lower limit. And what you get is that when you plug in the values, you will get, and watch the algebra, but this is the limit, as b tends to 0 plus of, this is 3 over 2. The 3 over 2 is this in the denominator coming out, and you get 1 minus b to the 2/3. So as b goes to 0, b to the 2/3 goes to 0. So the answer to this problem is 3 over 2. You see, we're approaching this axis, the y-axis, quickly enough so the area is finite, even though it is infinite there. Here's another one for you to do. Evaluate the integral from 0 to 2 of x to the minus 3 dx. You know what to do. Let's see how you did. Now, this integral has an infinite discontinuity at x equals 0, so this is going to be, again, the limit is b tends to 0, and you're going from 0 to 2, so here's where the b is. But you add 1 to the exponent and divide by the exponent, and this time you get minus 1 over 2x squared. And when you plug in the numbers, you get minus 1 over 8 plus 1 over 2b squared. Now the minus 1 over 8 is fine, but the limit as b tends to 0 from the right of 1 over 2b squared is positive infinity. So you see, this improper integral diverges. Now note, as you can see from the last two examples, here we had 3, and in the other one we had 1/3, that this case is different than the one where you have an infinite length. The theorem that we used there doesn't apply. So this is another thing, and there are things to be careful about. Here's another example for you. Determine if the following integral is convergent or divergent. If it is convergent, find its value. And you realize that this is a little bit of a clue. I would just probably ask you to evaluate this, and you would have to come up with that. Now your answer could just be it's divergent, but if it's convergent, you're finding its value. You know what to do. Let's see how you did. Okay, so now this one is discontinuous at 3. So this integral then is going to be the limit as t tends to 3 from the left, and you have the integral from 0 to t of this integrand. Add 1 to the exponent, divide by the new exponent, and you do have to do a use substitution here. But what you will get is that this is the limit as t tends to 3 from the left, and this is minus 2 square root of 3 minus x. We're valuing at 0 and t. Make sure you follow all these computations, because one day you will be doing this yourself. So when we put t in there, we get this expression. When we put 0 in, we will get this expression. And as t tends to 3, this part tends to 0. So the answer is 2 square root of 3. Some students will say that's the ugliest number they ever saw, but there are no ugly numbers, just like there are no ugly babies. So the limit exists, is finite, and the integral converges, and the value is 2 square root of 3. Another example, determine if the following integral is convergent or divergent. If convergent, find its value. Now this is an integral that goes from minus 2 to 3. This is 1 over x cubed dx. You know what to do. Let's see how you did. Well, there is a discontinuity, and you have to recognize that is at 0. And so what we're going to do, this is one of the cases, so you're going to look at the integral from minus 2 to 0. This is an improper integral, plus the integral from 0 to 3, another improper integral. So we have to check each one of these to see if they converge or diverge. And so what we're going to see is that when we evaluate this, and we'll just evaluate one of them, we'll just do this part of it. And so this is a limit as t tends to 0 from the left. This is from minus 2. Actually, yes, from the left, minus 2 to t, 1 over x cubed dx. Add 1 to the exponent, divide by the new exponent, plug those in and take the limit as t tends to 0 from the left, and you will get this. Now, when t tends to 0 from the left, this first thing goes to infinity, actually goes to minus infinity, so that's minus infinity. Now, we're really done. We don't have to evaluate the other, because if one of them is divergent, that means the whole one is divergent, so we don't have to bother with the second integral. Another example, determine if the following integral is convergent or divergent. The directions are starting to sound very familiar, aren't they? If it is convergent, find its value. We're going from 0 to infinity of 1 over x squared dx. You know what to do. Let's see how you did. Now this is actually doubly improper, because you see you have a 0 of the integrand at 0 and it's infinite in length. Wow. Okay, so we can split this up anywhere, but we're going to pick a value that's convenient for our calculation. So we're going to say that this integral is equal to the integral of the same integrand from 0 to 1, and then from 1 to infinity. Now this one here we know converges, because this was one of the first examples we did in an earlier lecture. But for this to be convergent, both of these have to be convergent, and so let's look at this one. And when we look at the integral from 0 to 1 of 1 over x squared, you put the t there. That's the limit as t tends to 0 from the right. You add 1 to the exponent, divide by the new exponent, plug t in, and you take the limit as t tends to 0. This is minus 1 plus 1 over t. This is plus infinity. So this integral diverges because this one diverges. Here's another problem. This is the integral from minus 1 to 2 of dx over x cubed. You know what to do. Let's see how you did. And what you can see is that this integral has the denominator becomes 0 at 0, which is inside of the interval. And so you can go from minus 1 to 0 of the integrand, plus the integral from 0 to 2 of the integrand. Now, you know that the second interval diverges because we've done that before. And so the original improper integral also diverges. And you see, this is if you're doing a problem, and I'm not going to say this is an improper integral, be careful and evaluate. I'm just going to be giving you a bunch of integrals to do, and I might give you this. Now, what students often will do is they won't realize this. The camouflage thing is that you have a 0 in between. They'll add 1 to the exponent, divide by the new exponent, and evaluate it at this. You can't do that because the fundamental theorem of calculus that we talked about insists that this is a continuous function. It's not. So this is incorrect, and you see this is a trap that many students fall into. Please be careful about this. Here's another problem. Evaluate from the integral from 0 to infinity dx over the square root of x times x plus 1. You know what to do. Let's see how you did. Let's see again how you did. This is a doubly improper integral. It is goes up to infinity here, and the interval is also infinite in length. So we have to split this at a convenient point, and we're going to pick x equal 1. Now that means this integral from 0 to infinity is going to be the same as the integral from 0 to 1, which in itself is going to be an improper integral, plus the integral from 1 to infinity, which also is an improper integral. And so what happens here is this is going to be, you have to have kind of a clever substitution that you use here. I'm not going to show you all the details, but make sure you work through the details. You're going to let u equal the square root of x. Now this is going to be the square root of x whole squared plus 1. And if you let the square root of x be u, then this is u squared plus 1, and this becomes du. So you see this really is an arctangent in both cases. So here you have the limit as b tends to 0 from the right of 2 arctan the square root of x, evaluated at b and 1. And this is the limit as c tends to infinity of 1 and c, and this is 2 arctan square root of x. Now it turns out that the arctan of 1 is pi over 4, and the arctan of 0 is 0, and so you get pi over 2 over here, because this is going to end up being, well, when you substitute those points in and evaluate b going to 0, this is what you will get. And if you do the calculation, it is pi. This is a finite area. Make sure you follow the calculations. Now, this is an improper application, but I wanted to talk to it because they're actually doing an arc length application, which is an upcoming topic that we have, but it involves an improper integral. So you see these things play together. And this is a nice problem, and it's a preview of a coming attraction coming very soon. So I'm not asking you to work on it because we haven't talked about that, but use the formula for arc length. I'll show you what it is, but we'll talk about it more in another video, to show that the circumference of a circle, x squared plus y squared equals 1, that's the unit circle of radius 1, is 2 pi. Well, the formula that we will derive later, if we apply it and do some algebra inside, we will get the integral from 0 to 1 dx over the square root of 1 minus x squared. Now this is a trig substitution, or actually this is also an integral that you can memorize. You could do it either way. But then this integral is going to be, again, it is improper because at 1 the denominator goes to 0. So we have to take the limit as b tends to 1 from the left. This is the arc sine of b over 1. And so this is going to be pi over 2 minus 0, and so the answer is pi over 2. Now we're going from 0 to 1. That's just 1/4 of the circle. They're going from 0 to 1. So that's just 1/4 of the circle. So you multiply this by 4, and you get that the total circumference of the circle is 2 pi, and that's the same thing as 2 pi r. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. We're all in this together. God bless you all.